Morning. How's it going? So, is the stream looking okay? It was looking kind of strange from my end for a second, but guess it's all right. Is everybody awake, or at least do you have some caffeine in front of you? Let's see. So who all's here? We have Caleb and oh, okay, cool. Yeah, let me know. There's been some hiccups, occasionally, but hopefully it continues to work all right. All right. Ah, Carolina. Cool. All right. So, and it looks like maybe we'll have a few more pop in as we get going. Um, I totally sympathize if you're finding, it's tough with the early morning section. Um, so today we're going to look more at momentum conservation. I have a few problems to talk about. I think this is a good example of a subject that's pretty easy to state, but the main sort of challenge of it, the main thing to learn is not how to state the problem, it's how to solve the problem. So we'll look at a few problems, and you'll see some of the ways that the algebra can get kind of annoying, but also how things that we can do to help to be sort of uh, you know um, very methodical with our processes for trying to solve problems, can help us keep organized, can kind of help us make sure that we don't confuse one term for another, one variable for another, things like that. So, okay, let's see. Before we jump into the next section, I wanted to do one more problem that kind of puts us, kind of sets the stage and is another example of momentum conservation. Um, so let me grab the problem. It's this problem. This one is kind of fun just because it gives us a few different things that we can talk about. So we'll look at this one and then we'll jump into collisions. So, okay. This kind of puts us back in sorry, a little more space. It kind of puts us back in the context of where we were on Monday, looking at situations where you have something that's in one dimension, something that starts with no momentum. So, okay, let me read this for you quickly. A 130 kilogram astronaut, including their spacesuit, obviously, acquires a speed of 2.5 meters per second by pushing off with his legs from a 1,700 kilogram space capsule. What is the change in speed of the space capsule? And then, if the push lasts a half a second, what is the average force exerted by each on the other? Um, and so we're going to use the initial position of the capsule as kind of the origin of our coordinate system. And then what is the kinetic energy of each after the push? So part of why I'm looking at this question is because we haven't been talking about energy, but when we start talking about collisions, one of the kinds of collisions involves conservation of kinetic energy. Okay, so this is a pretty simple problem. Basically, let's see, what are we looking for? In part A, we're trying to find the speed of uh, the capsule, the spaceship. Um, in part B, really what that's asking about is uh, to use impulse to find the force, average force. And then part C, kinetic energy. We know how to calculate kinetic energy, but this will be a good thing on which to review it. So first, let's draw ourselves a little cartoon. We have a space capsule and little astronaut dude, and they're gonna push off each other. I can't really draw that in any kind of meaningful way, but so then the capsule would be going one way, and the astronaut, of course, is going to be going the opposite direction. And, you know, they have some mass, and this thing has some mass. And similar to what we had already looked at, we kind of know immediately qualitatively that if the astronaut is going one way, the space capsule, the spaceship, is going to have to go in the exact opposite direction. Otherwise, there would be some net momentum in one direction, and that would violate momentum conservation because we've gone from a situation where the momentum initial is 0, and the momentum final after this guy pushes off also has to be 0. So let's state that in mathematical terms and come up with the velocity of the space capsule. So in other words, the initial momentum has to equal the final momentum. Initially, nothing's happening, so this is 0. And then after the fact, the two things are going to have to add up to 0. Let me put it this way, actually. Okay. So the final momentum, we're going to have the mass of the astronaut. We know his velocity, plus the mass of the spaceship times the velocity of the spaceship, which is what we're looking for. And so then we would solve this for Vs. We'll get minus ma Va over ms. And if we look at the actual numbers here, the mass of the astronaut is, so it's going to be negative this quantity, but 130 kilograms. His velocity is 2.5. The mass of the spaceship is, of course, much larger. And when we crunch this, we'll find that this is negative 0.19 meters per second. So in other words, the velocity of the spaceship is negative because it's in the opposite direction, and it's quite small compared to his velocity, and that makes sense because it's so much more massive. Okay, so that's kind of similar. Now, to find the average force, we need to make use of our definition of impulse. So the change in momentum, remember, was the integral of the force over time. But how we often make use of this is by saying that it's an average force times some time interval. And the time interval is 0.5 seconds. Second here. Sorry. So if we know the change in momentum, we can come up with the average time. So what was the change in momentum? For each, right? The mass of the velocity, the mass of the astronaut times his velocity is going to have to equal the average force on him times that change of time. So if we divide by the change of time, And let's put in our numbers. He weighed 130 kilograms. His velocity was 2.5 divided by half a second. We crunch those numbers. We'll find that this is 650 newtons. And so this was the force between them. The astronaut pushes with a force of this magnitude, and the spaceship pushes back with a force of that magnitude. Okay. And then the last bit, what's the kinetic energy of each? And this is kind of interesting. So we recall kinetic energy is 1/2 mv squared. So the kinetic energy of the astronaut is 1/2 his mass times his velocity squared. So 130, 2.5 squared. That's 410 joules. Whereas the kinetic energy of the spaceship is 1/2 times its mass, which was much bigger, times our velocity of the spaceship. Crunch that through, and we find that it's 75 joules. So it's kind of interesting. Although those two objects had to have the same momentum, because we needed to conserve momentum, it's not like they have the same energy. So it's kind of reminiscent of what we're going to get into when we talk about inelastic and elastic collisions. But in any case, this gives us this quick problem gives us a chance to kind of note the highlights of what we had talked about so far. Conservation of momentum when you start with zero momentum. A impulse. So this definition of impulse. And then we're getting into kinetic energy as well, will be in the mix. So let's see, question. Yeah, so how do you decide the direction? So for this, since it's one-dimensional, we could be more rigorous about it and say that the the astronaut is in the X direction, say, and then we would know immediately that the space capsule was in the negative X direction. We've been less careful than that, though, and just noted that in 1D, the sign tells you that they're opposite. So really the negative sign. But yeah, that's a good question. I don't want to say categorically that it doesn't matter, that you don't have to specify a direction. Because there's probably some circumstance where it would be helpful to solve the problem, but it's just not coming to mind. But I will, yeah, I guess with a lot of these more simple problems where it's just in one dimension, it doesn't necessarily matter. Yeah, exactly. You could assign a negative sign to the astronaut for sure. Then the other one would end up being positive, and that would show you that they're opposite. So yeah, that's a good question. I think as you practice this, you'll get a sense for how that works in one dimension. And we'll look at some more one-dimensional problems today. And yeah, it occurs to me that I'm not necessarily super careful with saying, hey, it's along the x-axis or it's along the y-axis. So I'll have to think about that if there are some circumstances where that causes problems. But yeah, that's an excellent question. Okay, so are there other questions about this problem? This is kind of where we're at. So where we're going is basically the middle sections of Chapter 9, and that's collisions. And really, there's not a ton of ideas here. There's basically three different kinds of, well, two main kinds of collisions. So an elastic collision, momentum and kinetic energy are conserved. An inelastic collision, momentum is conserved. Kinetic energy is not conserved. And then there's a subtype. So when we say that it's not conserved, this could mean anywhere from you lose a little bit of energy to you lose a lot of kinetic energy. It depends on the circumstances. And one special case of inelastic collisions is a completely inelastic or perfectly inelastic. And this is the situation where your objects stick together. So, in general, we have to, note what kind of collision it is, and then we can set up equations for conservation of momentum and conservation of energy, and then we can solve the problem. And different kinds of problems have a little bit different, tricks that we can use, and I'll show you a trick with elastic collisions in one dimension today. But that's it. I mean, there's not a lot of different ideas here. Like I said, the main task, the main meat to it is contending with the algebra sometimes. So let's look at some example problems. Oh, and here, let me give you sort of a cartoon of. Well, no, let's look at an example problem. So, yeah, yep, that the objects stick together. If you want to think of that as fusing together, that's a good way to think of it. It's basically you have two objects, they whack into each other, and you end up with something where they're connected. And it turns out that a lot of times these problems, completely inelastic problems, are a lot simpler because you only have one object to follow after the collision. So, and we'll look at a completely inelastic example, but let's start with an elastic collision example. So, let's see. All right. We have an elastic collision. So this is problem 35. A 0.45 kilogram hockey puck moving east with a speed of 4.8 meters per second has a head-on collision with a 0.9 kilogram puck initially at rest. I don't know how we get hockey pucks or pucks of different masses. It seems kind of silly, but in any case, assuming a perfectly elastic collision, what will be the speed and direction of each object after the collision? Okay, so notice, yeah, you had asked about the directions. We're using kind of this problem uses kind of the non-standard cardinal directions. So since it's in one dimension, um, it's a little, like I said, we're being a little less rigorous with our specifying directions. But the negative signs should allow us to keep things straight. So let me get my note here. One second. Let's set this up. So we have a puck, 0.54 kilograms. It has some initial velocity. And then it's going to hit into a 0.9 kilogram puck that's at rest. And, you know, we could set these up as calling this, if we're going to use the notation that they use in your book, mass A and mass B. How about we use that? And VA and VB, respectively. And so there's kind of a lot of things going to consider. Let's just write down what we know. So we know MA, MB, VA. Now we know VB too. It's at rest, so we can, another way of saying that is that VB is 0. And what we want to figure out is what is VA prime, what is VB prime. In other words, we want to know the speed and direction of each after the collision. Yeah, so, and a clarification, you might wonder, like, well, how do we know that this is in one dimension? Consider that the initial momentum is only in one direction. So in order to conserve momentum, we're going to have to be so that the final momentum is only in one direction as well. That's kind of how we know it's constrained. Okay. So we also know a couple other things. We know that since this is an elastic collision, kinetic energy is going to be conserved. And of course, momentum is conserved because momentum is conserved in all collisions. So this is helpful in that it just lets us write our conservation laws for momentum and energy. And so let's do that next. So let's look at energy conservation first. So very similar to how we had framed problems in the last chapter, we know that the kinetic energy initial is going to have to equal the kinetic energy final. What kinetic energies do we have? Well, we have 1/2 ma va squared. And this is going to have to be equal to 1/2 ma va prime squared plus 1/2 mb vb prime squared. So we know that. The other piece conservation law that we're going to take advantage of is momentum conservation. So we know that momentum initial is going to have to equal momentum final. So what does that look like? That will be ma va is going to have to equal ma va prime plus mb VB prime. Yeah, we're not considering any friction or work done by friction for this one. So we have basically two expressions. Two unknowns. So what do we do from here? We're going to do some algebra. So one way to go about this would be to try and eliminate, for example, VB from one of these expressions. So how might we go about doing that? You could imagine solving the top one for VB, but that'll have, these squared pieces. So how about let's solve for VB from 2 and then put it into 1. So excuse me. So what is VB prime? In terms of this stuff, we're going to have MA VA minus MA VA prime divided by MB. Okay. And then we can substitute that in to 1. See what happens here. So what's that going to look like? We'll have 1/2 MA VA squared. I'll try and be careful with my penmanship here. So 1/2 MA VA squared is going to equal 1/2 MA VA prime squared plus 1/2 MB. Now VB prime, we have this thing that we've substituted in. Okay. And I think you can already kind of sense how the algebra is going to get. We're going to have a lot of pieces floating around, but let's simplify things a little bit. We can eliminate this factor of 1/2 because it appears in everything. And the other thing I'm going to do is I'm going to just put everything on one side. So I'll subtract this piece over to the other side. And I'll subtract this over, and I'm going to expand this, what we substituted in that's been squared. So what is that going to look like? Well, we have MA VA prime squared, so that's this piece, plus, notice here we have an MB over an MB that's inside the square. So this is really a factor of 1 over MB. I'm just going to pull that out just so that I'm not writing it a bunch of times. And then in the numerator here, let's square that thing. So we'll have MA VA squared. We'll pick up 2 MA squared VA prime plus, and then the last bit we'll have plus MA squared VA prime squared. And then this first term, I'll subtract it over, MA VA squared. So this all is going to add up to 0. And let me reorganize this slightly. I think you see kind of what's going on or what's happened here. We have, I'll factor out all the rank, all the VA squared pieces, or VA prime squared. So VA prime squared times MA plus MA squared over MB. And then we're going to have pieces of order VA prime. So we're going to have a VA prime times this stuff. Let's see, 2 ma squared VA over MB. Sure that I'm not making any mistakes here. And then we'll have everything else, essentially. So what do we have? We have VA squared, and actually, so I can organize this a little bit. There will be one contribution from here, which will be the MA squared over MB, and then there's also this last bit, which is just a minus MA. Okay. So this is relatively gross. We have a fair amount of, just a lot of terms. But this, you can see, is a quadratic, where this is your A, this is your B, all of this would be your C. So you would need to solve quadratic. So in terms of how to do this exactly, you can see doing this in your calculator might get kind of messy because you have a lot of pieces. So I usually do stuff like this in MATLAB or do it in an environment where it's easier. Students have mentioned this thing, I think it's called Desmos. Really use whatever, environment that works well for you, but this would be a quadratic, so you'd have, you have to take those rather complicated pieces and then put them into the quadratic formula to extract the roots. And you would find that the roots for this are that VA prime can equal 4.8 or negative 1.6. And the question then is like, well, which root? And the answer is that if you look at this, VA prime being 4.8, that would mean that VA prime is the same thing as VA. So you don't want this one because then this would mean that they collide. They collide and nothing happens, which just doesn't make sense. So this would be the root that we would want. And then if we know VA prime, you can find VB prime. And so we could substitute that into our recall from equation 2, we had that VB prime equals MAVA minus MAVA prime. So now if we know that as well, you could solve this and find, you would find that VB prime is 3.2. Okay, so this this is an example of a elastic collision in one dimension. It gives you a sense of the starting point. You state your conservation equations for energy and momentum. The algebra can get, fairly complicated relative to what we've seen. It's not, conceptually, it's not complicated. We're just adding up momentum and energy. But you can see how if you have a lot of algebra, there's, mistakes and stuff you can get, you can run into issues. Let's see. What else would I want to mention? So the reason that we chose the negative 1.6, just to clarify, So if VA prime was 4.8, well, VA was also 4.8. So in order for that to work, VA prime being 4.8 would mean that VB prime would have to be 0. And that would be the same conditions as what we started with, which doesn't make any sense. It doesn't work for them to collide and for nothing to happen. So it's not a I don't think that's a you know it's a mathematical answer, but it's not an answer that makes sense. It's sort of like when we were looking at projectile motion, and you could solve quadratics and you would get negative times. It's like a time that it's a solution for your quadratic equation, but it's not a time that's realizable. So this would be an example of a result that doesn't, it works out mathematically, but it doesn't make sense conceptually. Let's see. How can you find the velocity without knowing the mass? Well, it depends on the problem. So yeah, so in general, if you had an elastic collision, notice in this one we weren't given either velocity, but we had two equations and two unknowns, so we could find them both. Presumably, if you have a problem where they don't give you one of the masses, they'll have to give you some other piece of information because you have two equations and two unknowns. So unless it's a bad problem, they have to give you enough information in order to solve it. It just may be that it's different information. So, but speaking of shortcuts, let me show you something that's helpful for one-dimensional elastic collisions. So this was rather involved because we ended up with a quadratic. So check this out. Yeah. So that homework question that you're mentioning, Caleb, if they give you one of the velocities, that's an additional piece of information. So you have a velocity. So there's one velocity that you don't know and one mass that you don't know. So I think you have enough information. It's just different information. So the algebra I think would look different, but it would be kind of the same procedure. You'd come up with two equations, and then you could, for example, substitute in for the mass to eliminate the mass. So I want to show you something for a one-dimensional elastic collisions. That's kind of cool. That should help with homework as well, and actually it helps with this problem. So the situation, let's think about just the general case. In general, suppose you just have like two masses. Let's see. VA prime and VB prime add up to VA. Is that how we check our answer? Well, there is a relationship between them. Yeah. I'm going to show you where that comes from in a second. Right now, actually. So suppose, let's just consider the general case for an elastic collision. You're going to know from momentum conservation that MA VA plus MB VB has to equal MA VA prime plus MB VB prime. You're also going to know from energy conservation that 1/2 MA VA squared plus 1/2 MB VB squared is going to equal this. Okay, so this is just the totally general case. Notice this factor of 1/2 appears everywhere. We can eliminate that. So we can reorganize this a little bit. Let me factor out. So let me call this 1 and 2. So from 1, let me factor out the what I'm going to do is I'm going to subtract, so we have all the MA pieces on one side. And factor it out. So, and then we'll put the MB pieces on one side. Okay. And then from the second one, I can do basically the same procedure. So I'm going to put all the MA pieces on one side. Okay. And notice these difference of squares, you can expand that, right? You know that that's VA minus VA prime times VA plus VA prime. Kind of the same situation here. So what we can do is take this and combine it with this, divide. Uh, 4 by 3. And notice the subtracted pieces and the masses are going to cancel. So if you divide this by this stuff's going to cancel. And this leaves you with this relationship that the sum of the masses of A equals the sum of the masses, or not masses, sorry, the sum of the velocities, A before and after, is going to equal the sum of the velocity of B before and after. And you can reorganize this. You can make it maybe a better way to express this would be to subtract the VB. So you can say VA minus VB equals VB minus VA. And so this is for, let me emphasize this. So this is a useful shortcut when you're solving problems that are one-dimensional for elastic collisions. And I can show you how useful this is. Notice, with the question that we had just talked about, just to recall here, so we only have about 5 minutes left, so I want to talk about one other question, or at least get it started. So, recall the hockey puck example. Yeah, so if you, now note, this is only for one-dimensional elastic collisions, but this can be a really powerful shortcut. And this is a good example of something that can help you solve problems. But notice that it only applies for one-dimensional collisions. So if we consider our hockey puck example again, just looking at the momentum conservation, if we make use of this expression, we can solve for VB prime. So notice VB was 0 in this situation. So VB prime is going to be VA plus VA prime. So we can eliminate VB prime in one step, basically, and then solve this thing for VA prime. So we would have to factor out, move some stuff around. Here, let me just add one step here. So notice we've taken that pretty messy quadratic expression that had a lot of terms to keep track of, and it's simplified down to just a few lines. So this is why I'm bringing this up to you. This is discussed in your book. This is equation 9.8. This thing. So this can be really helpful for one-dimensional elastic collisions. Okay, so questions about that? I think that's that gets to both of your questions about VA prime, VB prime adding up to VA, and in terms of a thing that can help you with homework questions. I want to spend the last couple minutes just setting up this inelastic problem. And then we'll have to solve it next time because I want to be better about respecting our class time. But let's at least state the problem. Yeah, like I said, if you have generally it's going to tell you if it's one-dimensional. I think in this situation, since one of the things wasn't moving, you know that the momentum before and after is going to be constrained to one dimension because there's only one before. With 2 dimensions, if you have objects that are both moving, it'll be totally clear that it's a 2-dimensional problem. But that's a good question. I have to think about that. I'm hesitant to speak categorically that's the case, but I'll think about your question, Carolina. So in the last minute or so, this is an example of a wait, no, this is not the question that I wanted to show. One second. We don't have time to solve it, but you can think about it and we'll solve it next time. But this is an example of an inelastic collision. So we were talking about what does that mean exactly? Well, it's a situation where things stick together. So in this question, you're going to have a sports car collides with another car and they stick together, and then they move off together. So we can, in this situation, in an inelastic collision, you're not going to conserve energy in the collision, but you will conserve momentum. And then we'll figure out, based on the speed of the combination of those two cars, we'll figure out how far they go. So it's sort of a practical problem, which is kind of cool. There's another very important inelastic collision question, which is the ballistic pendulum. And so we'll look at this. We'll solve this one next time. But also pay attention to the ballistic pendulum. there is a pretty involved homework problem that is about this. So the ballistic pendulum is addressed in example 9.11. So we'll talk about both of those. We'll talk about this problem next time, as well as looking in 2 dimensions. You're asking about 2-dimensional collisions. So yeah, that's what we had time for to get through today. We're getting into collisions. So we didn't get into 2D collisions, but we'll talk about that. We'll look at an example problem next time about that. You have some tools for dealing with one-dimensional elastic collisions. We've kind of distinguished between the different kinds of collisions, and we'll do some more practice with this tomorrow. So questions about what we talked about today? Okay. Yeah, if you guys work on homework together, that would be fantastic. You can set up a meeting on your among yourselves, and then yeah, get back to me with questions. Uh, and if you guys run into a question that's kind of that you're scratching your heads about, you can post about it in the homework questions channel on our Teams on Teams, and then we could kind of talk about it as a group as well. So, but I'm gonna sign off here shortly because I'm trying to be better about respecting the time schedule. And so get back to me if you have questions on Teams or whatever, and we'll do some more practice with this tomorrow. So uh, have an excellent day, and we will see you soon. Pendulum and vector problems. Yeah, uh, put a note about it on Teams, and we can talk about it together. If there's like I said, if there's a question that's kind of that you guys are finding, uh, that's tough. So, all right. Have a great day. See you later.